there is at least one flip-flop in every loop. All flip-flops have the same type of dynamic clock. All clock inputs of the flip-flops are driven by the same clock signal. This is a simple block diagram of a sequential circuit. So here these are the a number of flip-flops you can consider. This is the clock pulse. These are the inputs. Any kind of flip-flop you can consider depending upon your circuit. And this is a combinational circuit from where we can get the output. So some external inputs are there, and the flip-flop outputs also act as input for the combination circuit. So this is general block diagram of a sequential circuit. Now, depending on the nature of output, the sequential circuit are of two types. One is called Mealy mode, another is called Moore mode. Mealy mode or Mealy machine. What type of model is this? In this case, output depends on the current state as well as external input. Just like in the first figure here, this is the flip-flops outputs, and this is a combination of different network. The inputs are given here. So the output circuit combination logic network for the output, it depends on the external input as well as the flip-flop output. In case of Moore model, the output only depends on the current state of the flip-flop. These are the current state output of the flip-flop. So from there, inputs are taken for the output. So different combination of the current state may be considered in that network circuit. Synchronous sequential circuit model. We have to analyze the structure, then behavior, then circuit analysis and circuit synthesis. First, we consider one example of circuit analysis. Here, a circuit is given, a particular circuit is given here. Two flip-flop we consider, two JK flip-flop we consider. Outputs are denoted by A and B, and external input considered as X. So here, X is the external input, AB are the two outputs of the flip-flops, and here a combination circuit is given. 1, 2, 3, 4 are the AND gates, and another AND gate is considered for the final output. So here discrete way apps from here. Actually, the X is taken from that external input, and A and B bar is considered from that two flip-flops. Similarly, here the inputs are considered B bar, A bar from the actually given from the flip-flop outputs. So this is a typical simple example. So we have to analyze the circuit. So from this circuit, we can easily design the state table as well as state diagram. So what is the state table? So it depends on the present state A and B of the flip-flop, and what will be the next state that depends on the present state and the external input, whether X may be 0 or X may be 1. Here external input only 1, because of that X may be 0 or X may be 1. Based on that, we can find out the next state as well as we can find out the output based on the circuit design here. So if we consider the first present state, when we consider 0 0, at that time if we consider X is equal to 0, what will happen in this circuit? 0 0, X is 0. So X is 0 means here AND gate outputs are 0. Similarly here AND gate output of 3 and 4 AND gate output are 0. So 0 0 input, 0 0 input for the both flip. So at that time what will be the output? The previous output whatever there A and B, that is given here 0 0. Now when X is equal to 1, what is that output? When X is equal to 1 means B complement B is 0, so B complement is 1, so 1 1 here, and get 2 output is 1 and here is 0. So 0 1, so first the flip-flop output is 0. So A is 0, so next state A is 0. Now when B, so here A and B both are 0 0. So 0 means A complement is 1, X is 1. So 3 output and get 3 output is 1. So J is 1, K is 0. So for a JK flip-flop, J is 1, K is 0 means B is 1. So next step is here, B is 1 and A is 0. During that time, what is the final output for X is equal to 0 or X is equal to 1 in both cases? Here if you put X is Similarly, if you consider the present state 0, 1, same way by considering x is equal to 0 and x is equal to 1 from here, you can easily verify and easily find out the next step and final output like this. And similarly for 1, 0 and for 1, 1. So this is the state table for the given circuit. Now from the state table, you can easily design the state diagram. So here what is this? 0, 0, 0, 1, 1, 0, 1. These four are the four possible present state. Now, based on the combination of the present state and x, what will be the next step and what will be the output that is given here. So here 0 by 0, similarly 1 by 0, 1 by 0, 1 by 1, 1, these are denoted by x by 1, external input by output. So here first you could see 0, 0 present state means here it is 0, 0. Now when x is equal to 0 and at that time what is the next step? It will be 0, 0. So as x is 0 at that time what is the output? Output is also 0. So it is denoted by 0 and it is itself again after clock pulse remaining at 0, 0. So it is self-free. Look. So when present state is 0, 0, external input is 0, then external output will be 0 and next step will be 0, 0. So because of that it will be as it is with the same loop. Now when AB is 0, 0, if you give x is equal to 1, what is the next step? Next step will be 0, 1. So from 0, 0 it will go to 0, 1. At that time what is the output? Output will be 0 and x is input 1, so 1 by 0. Now present input is 0, 1 here. Now we are at 0, 1. When x is equal to 0, at that time where it will go? It will go to 1, 1. So from here it will go to 1, 1. At that time input is 0, output is also 0. So it is written by 0 by 0. If present input is 1, 0, next step will be 1, 0. So itself, so 1, 0 to 1, 0. At that time input is 0, output is 0. So because of that it is 0 by 0. Last one is 1, 1 present step. We are here 1, 1. What is x is equal to 0? If x is equal to 0, it will go to 1, 0. It will go to 1, 0. And what is the output? Output is 0. So 0 by 0. When x is equal to 1, then 1, 1 itself is in 1, 1. So if 1, 1 goes to next to 1, input is 1, output is 0. So this diagram is called the state diagram. Now from the state table as well as from the state diagram, we can find out the state equation. So state equation A t plus 1 is next step will be 1 and B t plus 1 is equal to next step for the second flip flop, that will be 1. When if you see here this A is this one, here A is also. So when x is equal to 0, A is 1, which case when AB present state 0, 1, 1, 0, 1. In this case when x is equal to 0, that means A complement B, AB complement plus AB into x is equal to 0 means x complement. So first 3, these are 1 and when x is equal to 1, at that case when present state is 1, 1, then output next state is 1. So AB into x, AB into x. So this is the first equation for the first flip flop. For the second flip flop, when B is 1, B in the first case only A complement B, x complement, A complement B, x complement. From the second, when x is equal to 1 in the first two and last. So 0, 0, 0, 1 and 1, 1 means A complement B complement plus A complement B plus AB plus AB into x. So these are the two equations for the two flip-flops. If you simplify these two equations simply, from equation 1 is get A t plus 1 is equal to bx complement into A complement plus B complement x into A. So if we assume that bx complement is equal to j, then we can write j a bar, and if you consider b complement x is equal to k, then k a. So this is the input of the jk flip flop. So this is the status of the next step of the first jk flip flop. For the second jk flip flop, this is a simplified equation, and this x complement x is equal to, you can write j, and AX complement is equal to K. So this is the next step for the second JK flip-flop. So this is the analysis of a particular circuit. If the particular circuit is given, from that we can design the state diagram, state table we can find out, as well as we can find out the state frequency. Now, if we want to design the circuit from a particular problem, the problem is given, from that how we design the circuit. Just reverse one, synthesis of the circuit. So first what we have to do? First step is we have to obtain the design specifications and study the same clearly to understand the operational behavior of the circuit. Step 2 is what? Construct a block diagram of the model, which what of the parameters are given based on that block diagram or the given diagram. Identify all the inputs and outputs, what are the inputs, what are the outputs that we have to find out. We have to draw the state diagram based on the information obtained from the above steps. Then we have to develop a state table from the state diagram. And here we have to check this state table to know whether it contains any state which can be eliminated. Means if there is any redundant state, means if for a particular state to go to another state and for another state to go to the same state, so one state can be eliminated. So we can reduce the circuit. That option we have to check. So after eliminating that redundant state, we have to develop a simplified state diagram. Then we have to develop the state assignment. Then we have to develop a present state, next state table. From that, we have to decide the type of memory element is, what type of flip-flop we have to use, that we have to find out. Then for that table, we have to find out the excitation table, present state next. From the present state next state table, we have to draw the excitation table for that flip-flop, the output map from the state 7 and 8, and simplify the excitation table and output function. Then finally we have to draw the synchronous systematic diagram, schematic diagram. Now here we consider one example of that design of serial binary adder. It is popularly we can use in our previous class simple binary adder circuit. Here we consider serial binary adder, parallel binary adder we have discussed earlier also, but carry loop ahead adder we have designed. So here how we can design a serial binary adder. Simply if we consider one example, A is a 4-bit number, A3, A2, A1, A0. B is another 4-bit number. The arbitrary number we have considered 1011, 1001. If we add first bit 11, so sum is 0, carry is 1. Then this 101 plus 1, 10, so carry 1. Again 101, carry here 0. So 11, 10, carry, final carry is 1. The result. So what is the total result? 0, 1, 0, 0 is the sum, 1 is final carry for this particular design. So what you have to do? So basically here next state decoder with circuit, we have two combination circuit is that there is a memory element and there is a output decoder circuit with sum and the carry. So here you see the sum of first two bits, what the carry is there, that is added with the next bit. So if we add any kind of flip flop we can use, the better, very easy way we can use D flip flop, because it gives a 1 bit delay. Because when you add these two numbers, so when you add suppose these two numbers, the previous bit carry is coming here, so 1 bit delay is there. So if you use a D flip flop, the circuit design will be very easy. So using D flip flop, we design this circuit for the binary. Now, AIBI you consider means I is equal to 0, 1, 2. A3, A2, A1, A0, B is simply BI is also B3, B2, B1, B0. So particular AIBI you consider what are possible combinations, suppose A0, B0. It may be 0, 0, 0, 1, 1, 0, 1, 1. 4 possible combinations for a particular bit, and for that carry may be 0 or carry may be 1. So carry 0, that is denoted by X, and carry is 1, that is denoted by Y. So how we can design the state diagram from here? So this is the carry X is equal to 0, this is carry Y is equal to 1. Now when you consider AIBI means simple any arbitrary bit. So AB, we have the external input here. What are the external input? A and B, because we want to add A and B, so this is one external input. What is the output? Final output is consider ZI is final output. So how we notation will be input by output. So here input will be 2 bit AI and BI, output is 1 bit, so ZI. So here, if we consider 0, 0, if we add, then what will happen? If we consider first, carry is 0. First is carry is 0. Then if we add 0, 0, then carry 0, means 0 plus 0 plus 0, output is 0. So what will happen? And there is no carry, carry is also 0. So it will loop is for self loop 0, 0, output is 0, self loop. If you consider 0, 1, 0 plus 1, 1, 1 plus 0, carry is 0. So 1 plus 0, 1. So if we consider 0, 1 input, then output is 1, but there is also no carry generated. So carry is also 0. 1 plus 0. 1 plus 0 is 1 plus carry 0. So 1 result is 1 and carry is also again 0. So for these three cases, the carry is 0. And for the last cases, 1 plus 1, 1 0 is there is a carry plus 0. So result is 0, but carry is 1. So when you give 1 1, result is 0 and carry goes from this to this step, carry is 1. Okay, now next when you consider carry is 1, now we are here if carry is 1. And again same procedure we follow, 0 plus 0, 0 plus carry 1. So result is 1, but 0 0, yes, 0 plus 0, 0 plus 1, 1. So result is 1, carry is 0, we are here. So carry is 0 means it will go to carry 0 here. So inputs are 0 0, output is 1. Here 0 1, 0 plus 1, 1 plus carry 1, so 1 0. There is a carry, so it will be within it here. So 0 1, carry is 1, output is 0. 1 0, 1 0, 1 plus 1, 1 0. So output is 0, carry is 1. When you consider 1 1, 1 plus 1, 1 0 plus 1 means carry 1, output is also 1. So this step 1 1, input, output is 1 and carry is also 1. So this is the state diagram. Here there is no option to simplify the circuit because there are two steps only here. Now from here we have to find out the state diagram, excitation table. So here one table we have shown the state table, excitation table. So here what are the external inputs? A and B are the external inputs. What is the present state? That is Ci minus 1 is the present state, Ci is the next state, output is Zi, and here we use D flip flop for D flip flop. This is excitation table from present state, next state we have defined the D flip flop. So first we consider what are the combinations of A, B and Ci minus 1. That combination I have written 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. From this state, from this present state and the inputs, we have to find out the next state Ci. So when 0 0 0, what will be the next step? Ci will be what? Just from this 0 0 0. So next state is also 0. So next state is also 0. 0 0 1, 0 0 1, 0 0 1. So next state is 0 0 1 is carried. So next state is 0 0 1 0, 0 1 carry 0, 0 1, 0 1 carry 0. What is the next step? 0. Next step 0. 0 1 carry 1, 0 1 carry 1 here, 0 1 carry 1. So carry will be again within this. So we have 0 1 carry 1. So next step is also 1. So like this, so all the other step I think you can easily find out what will be the next step. Similarly, what are the outputs for 0 0 0? Just from this diagram 0 0 0, so output is 0. 0 1 0, output is 1. So like this way, you can find out what are the outputs. Now you know the present state, next step. So what will be the output? What is the D input for the D flip flop? We know that in case of D flip flop, Qn plus 1 is equal to D. So here what was Ci, that is the next state is equal to D 0 0 0 0 0 0 1 1 like this. Easily D flip flop input you can find out. So this is the state table and excitation table. Now from this table, what you have to find out? The output Zi equation we have to find out, and B we have to find out. So Zi is equal to what? From this 0, 0, 0, what are the inputs here? A, B, Ci minus 1. So from here, we see what is the output. There is no loop here, diagonal elements are here. So Zi is equal to, simply, if we find out, simplify this. Remember, there is no possibility, so it will be A XOR of B XOR of Ci minus 1, and for B, B will be AI BI, BI Ci minus 1, Ci minus 1, A. M is AI. So what will be the circuit now? We get D and we get Z. So what is the output circuit? So this is AB. So this is C. C is equal to, from this equation easily find out. C means next step. So next step we can easily find out from here, just from this equation. And D is equal to, basically D, CI means this D, AI, BI, BI, CI, CI means A. So this OR gate. So C OR gate. So this is D. And what is final output? This is XOR of A, B, and Ci minus 1. A, B, Ci minus 1 XOR. So this is for a particular bit AI and BI. So if you consider for all the bits, AI means A3, A2, A1, A0, BI means B3, B2, B1, B0. So in that case, how we can design? So this is the final circuit. So Zi is equal to A XOR B XOR C, and D is equal to this. So this is nothing but a full adder. So this we can denote like this. Say a full adder. What are the three inputs are? A, B, Ci minus 1. Outputs are sum and carry. So here, two register is considered, which contain the 4 bits of A, another register for 4 bits of B. And here D flip flop, all the register and the flip flop are clocked by the same clock. Now one by when you give the clock pulse, one by one this bit will shift. AI, BI will add with this carry. A1, B1 will add with this carry. So it will simply add when you give a clock pulse, and final sum is the output. And this Ci is equal to gives the input of the D flip flop, and D flip flop output gives one bit delay to the input of the full adder. So this is the final circuit for binary serial adder. Okay. Now I have given a exercise for you. We have to reduce this state diagram and draw the logic circuit for the same. Here, too many states are there. If you see, if you analyze the states, then you can find some common states. That means you have redundant states are there. Then you have to simplify the state, and you have to redraw the state diagram. Then you have to redraw the state table, and from that reduced circuit, you have to find out the excitation table for a particular system, and then you have to draw the circuit. Here I have given the hint. This will be a final reduced state diagram,